All right, so today we are continuing our discussion of equations. That's our topic for the day, although we are going to branch out slightly from that towards the finish. And in your course notes, topics 2.4 to 2.11 are the ones that we're covering today. So, on Tuesday, I talked about solving equations, and what we were looking for was, if I gave you an equation with a variable, you were trying to find which values of the variable made that equation true. Right? And we saw some techniques. We solved a linear equation, and we saw how to solve quadratic equations. Okay, that's essentially what we did on Tuesday. And so the thing here was that this was our linear equation that we were looking at. So that was a linear equation, but the distinction I want to make now that I didn't make on Tuesday is that this linear equation has just one variable, right? It has the variable x in it. And so I can search, given the values of a and b, I can search for the value of x that makes that true. That's what we did on Tuesday. What we're going to do today is have a little look at equations of this form. Here, I could put it as y is equal to mx plus k, or ax plus by is equal to c. However you want to write that equation, they're all equivalent. But the important thing here is that we are looking at equations that have two variables, both x and y. Now, those variables appear to the power 1. They appear by themselves and to the power 1. And so we're going to call that a linear equation of two variables. Okay, so that makes it different to this one up here. And what you will see is when you have a linear equation of two variables, there are lots and lots and lots of values that will make that true. In fact, there's an infinite number of values that will satisfy this thing. And so what we can do is, if I choose the value for one variable, say x, then I can work out the variable for y that makes the equation true. As an example, here, imagine I have this linear equation in two variables. If I choose a value for x, actually I won't start with -2, I'll start here with 0 because that's an easy one for me. If x is 0, clearly y has to be equal to 3. Agreed? So the associated y value to make that equation true is 3. Likewise, if I put in -1, 2 times -1 is -2, -2 plus 3 is 1. -2 times 2... Sorry? Yeah, that's what I meant. No, I didn't. 3 minus 2 is 1. Sorry? Yeah, alrighty. Now if I go here, 2 times -2 is -4, -4 plus 3 is -1. That's what you were thinking? Yeah, you're doing the next one for me. There we go, -1. Likewise, I can choose x equal to 1 and I would get 5, x equal to 2 I would get 7, etc. You can see there's an infinite number of pairs of values for the variables that make that equation true. Okay, that's hopefully fairly straightforward. Actually, let me go over the other side of my etc. here. You can see at the moment I've chosen nice values for x, but I didn't have to. I could choose something like 1.5. What would I get then? I get 2 times 3 on 2 is 3, 3 plus 3 is 6. That way I've got a nice value for y. Let's choose an awful value for x. Let's choose something like square root of 2. Then the associated value for y that makes this equation true is 2 root 2 plus 3. And so on. I can do that for any value of x whatsoever. I can find the associated value for y. Now the thing is, we can think about this equation in two variables geometrically by thinking of these as being the coordinates of points. So we can think about equations in two variables geometrically via a coordinate plane. And the idea of thinking geometrically about equations, and vice versa, thinking about objects in the objects that we can draw in the plane, thinking about them as in terms of algebra, turns out to be a really, really super powerful idea. It was thought up about 400 years ago, and we've decided ever since then that it's really good. Okay, and so this idea is called coordinate geometry, in fact. So that's what we're getting into here. We're getting into coordinate geometry. So if I were to actually plot a few of these points, so let's put them over here so we can see them. For example, 0, 3. By convention, we put the value that we choose on the horizontal axis. So I'm going to use x on the horizontal axis. Since I was choosing x, the value that I work out, y, I'm going to put on the vertical axis. So we think of this as being the x-coordinate and the y-coordinate, horizontal coordinate, vertical. So here is the point 0, 3. X is 0, y is 3. Likewise, x is minus 1, at which point y is minus 1, 1. There's the point minus 1, 1, and so forth. Minus 2, minus 1, there it is. Minus 2, minus 1, and so forth. And if I were to do that for every possible x, this is the object that I would get. This is the shape that I would get. So in this case, it's a straight line. So we can say this is the graph associated with, so this is the graph associated with the equation y is equal to 2x plus 3 in here. Or if I wanted to, I could write that equation as 2x minus y plus 3 is equal to 0, or any other multitude of ways I could write that. Now it turns out that every linear equation of two variables, if I graph the values of the points that satisfy that equation, the graph always turns out to be a straight line. So the graph associated with any linear equation of two variables is a straight line. And of course, in fact, that's why it's called a linear equation, because it's a line. The graph is a straight line. And likewise, every straight line can be represented by a linear equation in two variables. So we've got a one-to-one correspondence in there. And that's nice. It turns out lines turn out to be a really useful idea. They crop up absolutely everywhere. I'll leave that for another day to see why lines turn out to be so useful. So, here are some equations in two variables. Let's draw the graph associated with each of these equations. So for the moment, all I'm expecting us to do is to choose some values for x and work out some associated values for y. And because I'm not very smart, I'll just choose some simple values for x to get me going. So minus 2 through to 2 will do me for the moment. So here in the first equation it is y is equal to minus 2x. So all I have to do is multiply this number by minus 2. So I'll go 4, 2, 0, minus 2, minus 4. Y is minus 2 times x, each case. Now, I think of each of these as being a point. Minus 2, 4 is a point. Minus 1, 2 is a point. 0, 0 is a point. 1, minus 2, and 2, minus 4. Plot them, and there's my graph. So let's do that. So there are my points. So let's go. Minus 2, 4 sits nicely there. Minus 1, 2. 0, 0. 1, minus 2. I can't quite fit the next one on, but anyway, that's probably enough. It's in the other one. Doesn't matter. Given that I haven't got my ruler with me, I forgot to bring it, we'll just pretend this is a straight line. That looks pretty straight, doesn't it? That'll do. Sit in here. So we would say that is the graph associated with y is equal to minus 2x. You can see it's a straight line. It's slightly, it slopes differently to this one, so forth, but there's the graph of 2x plus y is equal to 2x plus 3. Here's the graph of y is equal to minus 2x. Let's do the next one. It says y is equal to 2. That is an interesting thing. In this case, in the y equal to 2 case, so this is b, y is equal to 2. I want to think of that as a equation in two variables. So really, I'm actually thinking this is y is equal to 0 times x plus 2. Okay? Now, I can go through and do as we did before. Let's choose some values for x, work out the values for y. I'll do the same as I did with the other ones. So 0 times anything is 0. So I'm always going to get the answer no matter what value of x I put in. I'm always going to get the answer 2 in here. So this is going to be minus 2, 2, minus 1, 2, 0, 2, 1, 2, 2, 2, and so on. And I can plot all of those points quite happily. Minus 2, 2 sits me there. Minus 1, 2. 0, 2, 1, 2, 2, 2, and so on. Join them up. And there is my line for y equal to 2. Okay, have a look at the next one. So the next one is, can't even see what the next one is down there. It's x is equal to 3. So again, I want to think of that as being an equation in two variables. So if I write it the same as the other ones, it would be 0 times y. I'll say, what's the best way to write that? If I put that on that side, I might say that is equal to 3 minus x. Might be the best way to put that. So, let's think about this one for a bit. Here's x, here's y. What I was doing before was I was choosing a value for x to make that equation true. So, the left-hand side is 0. So there's only one value for x that I can actually choose that's going to make this thing true. 3. Because 3 minus 3 is 0. So if I choose x equal to 3, and I'll put it here just for the minute. What's the associated value for y? Well, it doesn't matter what value of y I put in there, this is going to work. 0 times 1 is 0. 0 times 2 is 0. So long as x is equal to 3, doesn't matter what value of y I choose. So I can, for example, here have 3 minus 2, that would work. 3 minus 1, 3, 0, 3, 1, 3, 2. They all work. And now I have a series of points. So let me plot those on my diagram here. I have 3 minus 2 there, 3 minus 1, 3, 0, 3, 1, 3, 2, and so on. And so you can see that, now I've got that arrow in the wrong spot, but this one's going to go up like this. So that will be the line, x is equal to 3. That one's the line, y is equal to 2. The last one I want to do here is 2x minus 4y is equal to 9. So D, I've got 2x minus 4y is equal to 9. I'll come back and do it over on this side. So here we go. 2x minus 4y. Let me choose the same values as we did before. We could choose others. In fact, I won't do that. What I'll do, these graphs, let me go this way. Let me just cross this out and say this. I recognise this as being a linear equation in two variables. This is a linear equation in two variables. So I know that its graph is going to be a straight line. So that tells me, that says the graph will be a line. So in fact, all I really need to do is just plot 2 points and join them up, and that will work. So I only need to plot 2 points, and then I can join them, and then join them up. And that will give me all the points on the graph. So let's choose x equal to 0. We've got to choose some values for x in here, and I reckon x is equal to 0 is probably as easy as I can do. So if I choose x equal to 0, then I have 0 minus 4y is equal to 9. So that tells me y is equal to 9 on minus 4. So minus 9 on 4. Minus 2 1/4, if you like. So there's 1 point on the line. 0 minus 9 on 4. Now look, I can choose another value for x. In here, it doesn't matter what I choose, x equal to 1, x equal to 2, or whatever. But again, I'm not very good at arithmetic, so I'm actually going to do to make my life easier, I'm actually going to choose the value for y and work out the value for x instead, just because it's easy to do. So in here, and as I said, I'm pretty good at arithmetic with 0, because I know 4 times 0 is 0. So that tells me then that 2x minus 0 is equal to 9. And so x must be equal to 9 on 2, so 4.5. And so now I have 2 points on the line, 0 minus 9 on 4, and 9 on 2, 0. And I'll join those up, and there will be my line. So let me put that over there. So 0 minus 2 1/4. So somewhere about here. So that value there is about minus 2 1/4. And the other one is 4.5, 0. So about here. 9 on 2. And now I have to try and join those up. And, sorry? Keeping me awake again? Yeah, cool. Okay, so here we go. And again, I should have brought my ruler with me, I thought I did. But here is the graph of 2x minus 4y is equal to 9, sitting there. So given the equation, we can find the associated graph for our linear equation. And now we can use our algebraic skills to find out things about these lines. And let's start off with a very simple question. I can say, does this point, 2 minus 4, which is conveniently not on my picture, should have chosen one that was on the picture, but anyway, 2 minus 4, does that lie on either of these lines? These lines aren't on the picture anyway, so it doesn't matter. So let's just use straight algebra skills. If the point 2 minus 4 is on the line, that tells me that those values, x equal to 2, y equal to minus 4, should satisfy the equation. So I can say, if 2 minus 4 is on the line, then the equation will be true when x is equal to 2 and y is equal to minus 4. That's our interpretation. So for part A, the left-hand side is 2x minus 3y minus 10. Let's put in x equal to 2 and y equal to minus 4. And I have 2 times 2 is 4. I have minus 3 times minus 4 is plus 12 minus 10. So I've got 16 minus 10. That's equal to 6. That is not the right-hand side. So that tells me that the point 2 minus 4, in fact, is not on that line. So 2 minus 4 is not on this line. Let's do part B. In this case, I guess we should have been checking. These are straight lines, x to the power 1, y to the power 1. So they're definitely linear equations in there. So B, the left-hand side is just y, and that becomes, when y is equal to minus 4, is just minus 4. So the left-hand side is minus 4. The right-hand side is a half x minus 5. When x is equal to 2, a half times 2 is 1. 1 minus 5 is equal to minus 4. They're equal, so the equation is true. So that tells me 2 minus 4 is on this line, in that case. So just by substituting in, we can tell whether our point is on the line or not. Yep?
That equation, does it mean that that line is the same, so all the points on that line are the same?
Say that to me again. What do you mean by the points are the same?
So that equation equals...
This one?
Yeah.
Yep.
Equals half x minus 5.
Yes.
So that means that that equation is true for that whole line.
Yes. Every point on the line satisfies this equation. Yes, that's correct. Yes. And so that would be one of the points on the line. Yep. And because this equation wasn't true, that point actually is not on the line. So what would happen is either when I put x equal to, if I put x equal to 2, if I was here, for example, on this line here, somehow on the line down here at minus 4, the line's going to miss it. It's either going to go above it or below it. Okay? Yeah.